Okay, so good morning, everyone. We're going to start today by introducing the fifth postulate. I've got the first four up here on the board already. We haven't used the famous fifth postulate yet, so let me write it and then I guess comment. The English is about 4 times longer than all the other postulates. So it says that if a straight line, you get the feeling he didn't think of this one for a while, right? Maybe this was the main innovation in axiomatizing geometry. Was the other postulates are kind of obvious, and then it was a big chore to figure out what more you could add to clean up the mess that existed before Euclid or something. I don't know the history. Maybe it's not clear how the development of these axioms worked. That would be pretty fascinating. So it says, if a straight line falling on two straight lines make the interior angles on the same side less than 2 right angles. I'll draw the picture. I think it was a good choice not to introduce this until we needed it, because we've seen in propositions 27 and 28 exactly the scenario that this comes up. If I'd stated it at the beginning, it would have been kind of like, well, who cares about this? Okay, so if you have two straight lines, maybe I should draw it like that. So two straight lines, try again, two straight lines, and a straight line falling on two straight lines, make the interior angles on the same side. So that means this, this, and this, less than 2 right angles. The two straight lines if produced indefinitely meet on that side on which the angles are less than the 2 right angles. So the side which I've indicated in the way that I've drawn the picture, on that side, if we continue the lines indefinitely, then they should meet. So dot, 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 i.e. this point here exists on that side. Okay, so we're going to use that in the proof of proposition 29, which is the next proposition to prove, in the following way. We're going to use it to reach a contradiction. So we will assume that two lines are parallel, but that these don't add up to, that they add up to something less than 2 right angles, and we'll derive a contradiction from the fact that they meet, and that's postulate 5, and the fact that we assume them parallel. So I guess you've probably heard of the fifth postulate of Euclid, and you know that it has a different relationship to the others, and that there are systems of geometry where it's false and so on. I don't really want to get into that right now, but are there any questions about the axiom itself? Okay, so I think I'll go straight to proposition 29 in that case. Maybe I'll recall briefly proposition 27 and 28. I think it's useful to do that. So these give sufficient conditions for lines to be parallel. So proposition 27, I'll just draw the pictures. It says that if a straight line falling on two straight lines make the alternate angles equal to one another, so that is this. So alternate angles means these two, then the straight lines will be parallel. So that's a sufficient condition for two lines to be parallel. Proposition 28 says that, well, it gives you 2 more. If a straight line falling on two straight lines make the exterior angle equal to the interior and opposite angle, so this is the exterior angle. If this is equal to that, then they're parallel. Or if the interior angles on the same side equal to two right angles, so that's either here and here, add up to two right angles, or here and here, add up to two right angles, then the lines are parallel. So that's three sufficient conditions for two straight lines to be parallel, and proposition 29 is the converse.
Does parallel just mean never meet?
Yeah, exactly. That's the definition. A straight line falling on parallel straight lines makes the alternate angles equal to one another. So the alternate angles equal to one another says, without loss of generality, that AGH is equal to GHD. So that's the converse to proposition 27. It continues, the exterior angle equal to the interior and opposite angle So that's the converse to the first part of proposition 28. I guess that was blue. And the interior angles on the same side equal to two right angles. So that's here and here, adding up to two right angles. Okay, proof. So we start with the green, the alternate angles being equal to one another. Suppose for a contradiction, now this is not how Euclid says such a thing. He says something like, for if they were unequal, ... then that's impossible. Suppose for a contradiction that AGH is not equal to GHD. Then one is larger. Without loss of generality, we can suppose that it's AGH. Okay, well, so we're comparing AGH and GHD. Let BGH be added to each. Well, by proposition 13, which says that if you draw a straight line to any other straight line, the sum of the two angles that it makes is two right angles. So by that proposition, if I combine AGH and BGH, is two right angles. And since AGH is greater than GHD, one of the common notions to do with addition gives us that if I add BGH, then that's greater than GHD combined with BGH. And you can see the fifth postulate looming now. So that says GHD plus BGH is less than 2 right angles. So by the postulate we just discussed, those 2 lines must meet somewhere out here. But that's a contradiction because they were assumed to be parallel. So in fact, it must be the case that AGH is equal to GHD. So, no thank you. All right, so that's the first part. It still remains to prove the other 2 assertions, but are there any questions about this part? All right, so I'll move to the other boards. Just give me a second.
Hey, Dan, and some of your diagram is cut off in the orb cam.
Oh, really? Oh,
The A and the C is not visible, but the rest of the diagram is fine.
that's interesting. On the recording machine, the orb cam sees that fine, so I wonder what's going on.
Oh, okay, so it's different from what I'm saying. Okay.
Well, let me try to get it back and see if that helps. Could be, of course, the size of the monitors being different or something, but that would be...
Well, I
Is
mean,
that
as
any
long
different?
as it's correct on the recording, is fine, right?
Well, yeah, we'll discuss that later. I'd like it to be visible to everybody, of course. Can you see that now or still no?
Let me check. The A and the C are still off screen. I mean, I can't adjust anything, right? It's just okay. Anyway, just let me.
Ken, are you on your computer or on your
I'm on
tablet?
iPad. Oh,
Oh.
maybe it's my iPad. Yeah.
Well,
Okay.
yeah, we'll try and fix that later. Yeah, thanks.
Cool.
Okay. Okay, so we've proven that AGH is equal to GHD. So I have to prove that EGB is equal to GHD, and that the sum of BGH and GHD is 2 right angles. Okay. So we have that AGH equals EGB. That's by proposition 15. Therefore, by what we already proved, and transitivity of equality, EGB is equal to GHD. So that was not difficult. Now let BGH be added to each. So that means that EGB, BGH is equal to BGH, GHD. But again, by, I guess it's proposition 13, EGB, BGH is 2 right angles. So we're done. We've proven that the sum of these 2 angles is two right angles. So that completes the proof of proposition 29. So over to you, Ken.
All right. Cool. Thanks, Dan. I think my proposition is a little bit shorter than your one. I'll take up, maybe I'll use the remainder of the first board to state the proposition and then use the second board to prove it. Since we can see both boards now, I think that's probably safe to do, right? Okay, so proposition 30. Oh, I'm on white now. Excellent. Okay, so this is essentially the transitivity property for parallel lines. So straight lines parallel to the same straight line are parallel to each other. And parallel to the same straight line are parallel to each other. Okay, so it's going to be interesting to mark on the diagram. So I'm going to have three sets of, I'm going to have a straight line here. I'm trying to decide whether I should go to the next board for this. This is not quite enough space for the diagram. I'll go to the next board for the diagram since I'll need to refer to it during the proof anyway. So, right, the statement is straight lines parallel to the same straight line are parallel to each other. So I'm going to have three straight lines. One, right, two, and three straight lines. And I'm going to have, obviously, a line crossing them because I'm going to need to use the angles coming from the intersection of this line and the three lines to make some deductions. And, and I'll label these lines A, B, E, F, C, D, A, B, E, F, C, D. And the reason why I'm labeling it in this reverse way is that AB is going to be assumed to be parallel to EF, and CD is going to be assumed to be parallel to EF, and we're going to try to conclude that AB is parallel to CD. So EF is the line that all the other lines are parallel to. So the intersection points we'll label G, H, and K. Again, slight inversion of, oh no, that's fine. Right. So, so we're going to assume, I'm going to mark it in the diagram, we're going to assume that AB is parallel to EF. I'll mark these with two red markers there. I'm going to assume that EF is, well, CD is parallel to EF. Okay. So the statement here is that if AB is parallel to EF and CD is also parallel to EF, then AB is parallel to CD. Okay, so the proof is going to be using mostly proposition 29, as we might expect, because that's when Dan told us all these conditions for showing when when lines are parallel. Okay, so so by proposition 29, the angles AGH. So we're gonna do this. The angles AGH and GHF are equal. So I think I missed a word there. I should have said the alternate angles. And I'll mark them on the diagram. AGH is this one, and the GHF is this one, right? So they're alternating angles on the set of parallel lines, AB and EF, so they're equal. And we also assume that the other two sets of lines are parallel. So again, we're going to use, well, I'll just mark the angles in here now, right? So these two are also equal. So actually, I'm thinking I've mislabeled the propositions, right? Because proposition 29 is the converse, right? Anyway, Dan, if I've gotten the numberings wrong, you might want to correct me. Right. So
No,
I'm
no,
gonna
that's
say
fine.
no.
The
Okay.
proposition 27 and 28 said you can deduce from those angles being equal that
Oh,
they're parallel.
oh, actually, I had it wrong in my head. All right, got it. All right, so okay, so that then it all makes sense. So the corresponding angles. So I'm going to use this terminology that Euclid doesn't use, but we use in high school to talk about the blue angles I've marked, which are the corresponding angles GHF, right? GHF, and the other one, which is HKD, are equal. So this is, I'm not saying it again, but this is again using proposition 29. But what I will say is that the angle GHF, right, this is what Euclid calls the external angle. And HKD is what Euclid calls the opposite internal angle. Right, so so whenever Euclid's talking about corresponding angles, he'll refer to an external angle and the opposite internal angle. And if the lines are parallel, then they're equal, which is the statement that I'm using here to conclude that these two angles, GHF and HKD, are equal. And so now we've got all the marked angles being equal. So now we look at A, B, and CD and note that so now we're looking at A, B, and CD since the angle AGH is equal to, I guess I can write the whole thing, right? GHF, right? And that's equal to HKD. So these are alternate on A, B, and CD, right? So these, well, I should say that, yeah, I'll just say by proposition 27, AB is parallel to CD. And I'll just note here that in brackets, I guess I missed this when I was writing the sentence, right? AGH and HKD are alternate angles on the lines AB, CD. Maybe not the best way of saying it, but the alternate angles on A, B, and CD formed by the intersecting line GHK. And so, yeah, proposition 27 says that if you have alternate angles being equal, then the lines that form them are parallel. And so that's proposition 30.
Awesome. We even have 5 minutes left over.
Yeah.
What do you think of the two boards instead of one?
I think it's great because previously on the second board, on the first row, it was kind of on an angle, and it was hard to well, it wasn't hard to see, but like there was just a funny angle here. Here, I can be assured that the audience can see both boards. So if I have a diagram on the previous board, I can refer to it without I have it in my notes, right? But then I don't have to worry about reproducing the diagram. And I think that's great.
Yeah, Ethan was suggesting having a slider so we could sort of zoom in and out a bit if the boards don't fit on the screen. So maybe that would.
Yeah, this is probably just my iPad being not wide enough.
No, I have the same issue on my iPad. The thing is, the boards are actually sized perfectly to be the aspect ratio of an iPad. So.
Oh right. Oh, each board by itself.
Yeah, that's right. So.
Right.
I guess that means that when you zoom out a bit, there's sort of a different amount of space on the sides on the laptop screen, which is a different aspect ratio. So, or on the monitor. Right. So it wasn't noticeable so much with a single board, but I mean, I could fudge around with the orb's position to try and make it fit on all the devices, but I think it's probably worth having a slider that you can adjust yourself anyway.
Okay, yeah, cool.
I was a bit worried with the two boards that the writing would be too small, but in practice, I think it's not. So I think this is. I think we'll stick with this. Yeah.
Yeah, cool, nice.
All right. What's up next? We have a tea break, or is it? Yes.
Nah, it's SLT first, and then I know because I have to go during your tea break.
All right.
I have a question about about Euclid.
Yeah.
How did he decide like what to prove? Are we proving all these things for like one big proof, or yeah, I don't know.
I think all of this, or most of this, existed before Euclid. So he was synthesizing a sort of unruly collection of facts spread across many books, or maybe not even in books. And so he chose what to put in and what to leave out, and added some axioms and proved some new things. But I think he was figuring out how to systematize an existing body of geometry to a large extent. I mean, keep in mind that Euclid is hundreds of years after Pythagoras, or maybe 100 years. I don't know. So there was plenty of stuff out there. I don't know if he had in mind a single theorem he wanted to get to. I haven't read the rest of the books, so yeah, I don't know if there was a maybe the Pythagorean theorem is kind of what we're building to. I don't know if there's a point
Cool.
to each book or something.
I didn't look far enough ahead to know this actually.
I feel like at the moment it feels like we're kind of learning the basics, right? How angles work, the relation between angles and side lengths, how parallel lines work, the relation between, and there's like a bunch of connections between different concepts we're building up, right? Between angles, lengths, the notion of parallel, and I guess we're going to do something with it, presumably, but I don't know when that happens. Let's have a look. Book 1 ends with proposition 48, which says, if in a triangle the square on one of the sides is be equal to the squares on the remaining two sides. Oh, proposition 47 is the Pythagorean theorem.
Oh, there you go.
So yeah, I guess that's good. So we're building to the proof of the Pythagorean theorem. Yeah, good question. That would have been
Which one is
good
Pythagoras? This is a squared plus b squared equals c squared?
Yeah, isn't that? Let me read proposition 47 and make sure the diagram looks correct. In right-angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle.
All right, there you go. I guess we haven't done squarings yet, right? It'd be interesting to. Yeah. Okay. Cool. Nice.
So I think it's going to happen pretty fast, right? I mean, from proposition 30 to 48, we're going to get a lot done. So I reckon the next several weeks are going to we'll sort of set up a lot of machinery that we're now going to exploit, I guess.
Cool. Nice. I guess yeah, I I didn't know that's where we're going, but this is cool.